So first of all, let me thank the organizers for inviting me to give a talk here. It's a pleasure to be here. I would also like to thank Ulrike Tillman for giving such a good introduction to the subject, because my talk will be on the same theme. So this is, in some sense, a sequel to the Madsen-Weiss solution to the Mumford conjecture. So it's about diffeomorphisms of manifolds. So to fix a notation, M will be a smooth compact manifold. And then we have the diffeomorphism group. Of the manifold. And as we heard in Ulrike's talk, the classifying space of the diffeomorphism group is can be thought of as a certain moduli space. It's the classifying space for smooth bundles with fiber diffeomorphic to M. So what does that mean? It means that if you have a manifold X, then if you look at the space of, if you look at the set of homotopy classes of maps from X into this space, then that's in bijection with the set of smooth fiber bundles with fiber diffeomorphic to M modulo isomorphisms of such bundles. So in particular, just as Ulrike explained, it's desirable to know what the cohomology of this moduli space is. For instance, because this is the ring of characteristic classes of such bundles because of this relation. So the question is, well, can we calculate this for a given manifold M? And this is, in general, a very hard problem. I'd also like to consider a variation. Diffeomorphisms are not the only kind of automorphisms manifolds that there are. So you can, of course, look at homeomorphisms, or well, the weakest form of automorphisms would be what I'll denote by auto M. This is the space of homotopy self-equivalences of M. So it's not a group, but it's a group-like topological monoid, and it also has a classifying space. And this time, this classifies general fibrations with fiber homotopy equivalent to manifold M in a similar sense. And so we could also ask what is the cohomology ring of this moduli space. And so those would give you characteristic classes for fibrations with fiber homotopy equivalent to M. And then, supposing you can compute these things, you can ask what's the relation between these two objects. Because there's an obvious map, well, the diffeomorphism group includes into the homotopy equivalences. So in cohomology, you get a map from this cohomology ring to the cohomology of the B diff. And you can ask what that map is. So, of course, this is a very difficult problem in general. You wouldn't expect to be able to solve this for a given manifold. So, well, I'm going to make some restrictions. So today I'm going to be considering a highly connected manifold, by which I mean that it's a d-1 connected and 2D dimensional for some d. So this is high connectivity, and I'm going to restrict to Q coefficients in my cohomologies. And there's a particular example of such a manifold that appeared already in Ulrike's talk. In her talk it was denoted WG, I'll denote it by MG, and it's obtained by taking a G-fold connected sum of the manifold SD equals SD. And for technical reasons, I'll also consider what I'll call MG1, which is the manifold with boundary I obtain by removing an open disk from this closed manifold. So one thing you can start asking is, well, how can we produce classes in this cohomology ring? So let me tell you about one way of doing that. So from now on, I'm going to assume that my manifold is oriented. So diffeomorphisms will be orientation preserving. I'll also assume that if it has a boundary, then all my automorphisms restrict to the identity on the boundary. So if I have so here's a way. So if you have, so remember this is the classifying space for smooth bundles. And if I take such a bundle with fiber, my 2D dimensional manifold, I'm going to assume it's oriented, and then I get an orientation of the fiber-wise tangent bundle. So this is a 2D dimensional oriented vector bundle over E. It's the kernel of the differential of this map. So this is classified by a map from E to B, so 2D. And so if I give myself a characteristic class of oriented vector bundles, so an element in this cohomology ring. So now rationally this is of course nothing but a polynomial ring in the Pontryagin classes and the Euler class. And given the C, I can take this characteristic class of this bundle, and that will then be a cohomology class in E. And then I can do a push forward or integration along the fiber along this map pi. And since the fiber is 2D dimensional, this will shift the dimension in this way. And I get a cohomology class on X. And so I'll let kappa C of this bundle be the image of this cohomology class here. So right. And now this you can do for any bundle, and so there's you can do this in the universal for the universal bundle where X is equal to B diff. And so I'll just denote the you have a universal class kappa of C that lives in the cohomology of V diff. Like that. So what you need to take away here is that for any cohomology class in here, you get a cohomology class in BDIF. So now, of course, there's nothing a priori to guarantee that this is I mean, what can you say about the sort of the subring generated by all these classes? Does it generate the whole thing, or even, I mean, are there dependencies among these classes? There might very well be. Okay, but then let's recall what Madsen and Weiss proved. So this is in the case when d equals to 1. So what's a highly connected manifold in this case? Well, highly connected in this case means just zero connected, so connected. And this MG, and I just happen to have written down all the examples of such manifolds by looking at these MGs. So this is just an oriented closed genus G surface. Now there's a remarkable coincidence that happens in this case, namely, if so I'm going to assume that the genus is at least 2. So the diffeomorphism group, it always includes into the homotopy equivalences, and in this situation, this turns out to be a homotopy equivalence, in fact. So so then you can say that there's no difference between characteristic classes of smooth bundles and characteristic classes of just vibrations in this setting. So there's another coincidence, namely that the components of this topological group are all contractible. So this is in fact also equivalent to what was denoted by gamma G in Ulrike's talk. So this is just a mapping class group, so discrete group. And as Ulrike mentioned as well, we have this homology stability that was originally proved by Harrer, and then with the exact range improved later by Ivanov, and then later improved even more by Boltzmann, saying that if you take the kth homology group of the classifying space of this mapping class group, there's a certain map that increases genus by 1, and this is an isomorphism in a certain range if G is big enough, and the range is G is greater than or equal to this amount. So if you fix K, then if you let G be big enough, this will be independent of G. So if you haven't seen this before, what's this map? Well, it's not difficult to describe, or at least the idea. If I have a genus G surface with one boundary component, I can increase the genus by gluing on a torus like this with 2 boundary components. And if I have a diffeomorphism of the first surface, then remember I said that my diffeomorphisms are assumed to restrict to the identity on the boundary. So my diffeomorphism here would be the identity here, and then I can just extend it by the identity on this added piece, and that describes this map. So the homology stabilizes, and so what is the stable cohomology? And that was conjectured by Mumford and proved by Madsen and Weiss. So if we let G go to infinity, and if we look at the cohomology ring, so I'll just write gamma infinity for the stable cohomology, the limit as G goes to infinity of these things. This is actually isomorphic to the polynomial ring on the kappa classes, where kappa I is the characteristic class associated to the I plus first power of the Euler clause. So C equal to e to the I plus first power. So, okay, so that's the description that we have for surfaces. So now one can ask what happens in higher dimensions. So in this case, this happy coincidence that we had over there does not happen. So the diffeomorphism group is not equivalent to the homotopy equivalences. So this means that now we have to deal with two problems instead of just one. And there is a version of the parastability theorem. So and there's one for each. And the funny thing is that they stabilize at the same, or at least the currently the known range is the same. It might be possible to improve, but both the homology of the automorphisms and homology of the diffeomorphisms stabilize for G greater than 2k plus 4. So this is due to myself and E. Madsen with rational coefficients, and there's an integral version for the diffeomorphism group by Galatius and Oscar Randall Williams. So integral statement for the diffeomorphism group. We don't know whether the integral homology of the homotopy equivalences whether that stabilizes, or I don't know. Okay, so then now there are two stable cohomology rings to calculate, and so historically it's sort of turned around, because for the case of surfaces, the homological stability theorem was proved first, and then the stable cohomology was calculated. In this case, the history is turned around, because Søren Galatius and Oscar Randall Williams, they first calculated the stable cohomology, and then later this stability theorem was proved. So let me state their results. So Galatius and Randall Williams, they proved that in fact, if we let t go to infinity, for the diffeomorphisms, this is isomorphic again to a polynomial algebra in certain kappa classes. And I have to specify a certain set of cohomology classes in BSO2D. So C is a monomial in certain Pontryagin classes, and you have to throw away some low ones. So this is a precise statement. So you throw away everything below this, but then you look at all monomials in these classes in this polynomial ring, and you form the kappa class according to this construction. Then you get the characteristic class here, and then the theorem says that in the stable range you get a polynomial algebra in those classes. So this actually extends. This extends the Madsen-Weiss description. Yes, thank you. Sorry. So this is for D different from 2. Good. So what I want to tell you about now is a more recent result due to myself and E. Madsen. So it's about the calculation of the stable cohomology of the homotopy equivalences. So it's a little, you can't state it in as briefly as you can do it here, but so this is what I'll try to explain during the rest of the talk, is how you can actually calculate this. So, and I also want to say that, well, we have this map, and both of these are in some sense calculated, but what is this map? So I want to convince you that this is something that should be, I want to convince you that this is an interesting map to be considering. So more about that later. So okay, I'll just say, well, calculated or so the reason we don't understand this map is that because the calculations are very different in nature. So to approach this, so this will use heavily rational homotopy theory, and so let me just briefly recall some facts about rational homotopy theory. So if you have a connected space X, let's look at its one connected cover, or universal cover if you like. Then you have equivalence, a differential graded Lie algebra, lambda of X tilde. So this is equivalent, define this for any simply connected space. And what are its properties? Well, if you look at the homology of this, I mean, it's a differential graded Lie algebra, so it has a differential, and just taking the homology with respect to that differential, you get the rational homotopy groups of your space, shifted by 1. And moreover, the Lie algebra structure here corresponds to the Whitehead product on the homotopy groups. So you can read off, in principle, the rational homotopy groups if you know a model for equivalence, e.g. Lie algebra. You can also read off the cohomology of the space. If you take the Chevalier-Eilenberg cohomology of this differential graded Lie algebra, this will be isomorphic to just the rational cohomology of the space. As an algebra. So in particular, you can derive a spectral sequence from this. So there's a spectral sequence going from the I'm going to stop writing out tensor Q all the time. So these are the rational homotopy groups. From the so this is a graded Lie algebra with the Whitehead product. You can take its Chevalier-Eilenberg cohomology, and there's a spectral sequence from that to the cohomology of the one connected cover. And in fact, of course, you have an action of the fundamental group on the universal cover. So this is in fact a spectral sequence of pi 1 x modules. Okay. So what I'm trying to get at is trying to calculate the cohomology of the space X from knowledge of its homotopy groups. So this calculates, in principle, the cohomology of the universal cover. But how do you get to the whole space? Well, of course, you also have the usual spectral sequence of the vibration defining the one connected cover. If you just look at the Serre spectral sequence of this, then you get a spectral sequence converting from the cohomology of the fundamental group with coefficients in this local system converting to the cohomology of X. Okay. So these are two spectral sequences that you have for any connected space. And as input, you have the homotopy groups, the Russian homotopy groups, and the fundamental group of your space. So I'll state a theorem now. I'm not going to state it in the generality that we have it in, but in order to make the exposition a bit, in order not to be forced to introduce lots of heavy notation. So let X be the classifying space of this homotopy equivalences of MG1. And I'll just state the theorem in the case when D is odd and greater than 1, and the genus will be greater than 1. So the first statement is that Euler's DGLE algebra of the universal cover here is actually formal as a differential graded Lie algebra. So it can be connected by a zigzag or quasi-isomorphisms of differential graded Lie algebra to its own homology. So in particular, I should have given these spectral sequences names. So I'll call this 1, and I'll call this 2. So this implies, and it's in fact stronger than, but it implies collapse of the spectral sequence at E2. The second statement is about the second spectral sequence. It also collapses at E2. But here I have to introduce, well, it collapses at least in the stable range. So the first statement is just assuming D greater than 1. It's an unstable statement.
First one collapse.
This is supposed to be 2. Yeah. Right. So the stable range, I recall, it's G greater than 2k. Well, or 2 times the cohomological dimension plus 4. And so that's great. Both these spectral sequences collapses, at least in the stable range. Now, so we need now just to calculate the homotopy groups. So third statement is that, well, pi 1 now of this B what? It maps surjectively onto, so now I'm stating it in the case when D is odd. There will be another group in other cases. It maps surjectively onto the symplectic group with finite kernel. And then for the Lie algebra, this Lie algebra turns out to be isomorphic to a certain Lie algebra of derivations. So what do I mean by this? So this is the Lie algebra. This is the graded Lie algebra. Of the plus stands for positive degree. And this is a free Lie algebra on these generators. And this omega stands, well, it's supposed to signify that the derivations annihilate the element omega, which is, well, in some sense, the symplectic form. And the degrees of the generators, so this is the free graded Lie algebra. The degrees of these elements are d minus 1. Okay, so that's yeah, this is my notation for the free Lie algebra, free graded Lie algebra. So there's a difference if these, I mean, there's a difference between the even case and the odd case. So that's the statement of the theorem in this case. So I'll just add a remark that there is a more general theorem for arbitrary highly connected manifolds. So let's see, 2 doesn't really make sense for arbitrary manifolds because there's no G. But the other statements, they hold more generally for any highly connected manifold, in the sense that I explained in the beginning. And actually, since I'm dealing with just homotopy equivalences, I only need Poincare duality spaces. So you have to, in this case, the fundamental group will be not isomorphic to, but up to finite groups. I mean, it will be commensurable to the automorphisms of the middle dimensional homology with the intersection form of the manifold.
So what do you mean by highly connected? Do you mean up to the middle dimension?
Yeah, so d minus 1 connected to the dimensional. And the appropriate replacement for this derivation, Lie algebra, is still a Lie algebra derivations on a free Lie algebra on I guess take the middle dimensional cohomology, and you can interpret the intersection form as an element in here, and Um, yeah, so you can interpret the intersection form as an element in the Lie algebra, and you can look at derivations that kill that element. Okay, but this is the...
Again, you're assuming D odd.
no, this is actually true also for D even. So in this, I mean, so for this manifold, if D is even, you would replace the symplectic group by an orthogonal group. Yeah. Okay, good. So I should say one or two words about the proof. So of course, let's see, maybe I go here. So some words about the proof. I'll just say some of the ingredients. So first of all, for the first statement, this formality statement, this really uses the classification of vibrations in the category of differential graded Lie algebras. So it uses that and the full force of Quillen's rational homotopy theory, which states that the rational homotopy category of simply connected spaces is equivalent to the homotopy category of differential graded Lie algebras. So, and this classification of vibrations, I mean, it's not so surprising that derivations show up, because if you think about what vibrations of Lie algebras are, they're basically, I mean, you can reduce it to extensions of Lie algebras, and extensions of Lie algebras are basically classified by derivations. So it shouldn't be too surprising that derivations show up. And there are a number of people who have, I mean, this sort of goes way back. I mean, you can already see this in Sullivan's paper, and certainly Schlesinger and Stashev, and Tonray should be mentioned. And there's also a recent paper by Andrei Lazarev, which explains this in the language of L-infinity algebras. So some more recent contribution to this subject. But that's basically all I'm going to say about one. It also involves constructing a non-trivial L-infinity quasi-isomorphism from this DG Lie algebra to its homology. But I won't say anything more about that. I mean, well, so that is just, I mean, it's not immediate from this. You have to do a little bit more extra work. But it's essentially due to that we have these models for, I mean, that we have this classification of vibrations in differential graded Lie algebras.
Which vibration are you applying that to?
This is to identify the homotopy type of B aught.
Yeah.
So
you're using, which vibration are you applying this classification to? I just don't understand. I mean, if you told us that about any, you could, I mean, you would convince me that every manifold, every space was formed, which isn't, I mean, I don't know how you're using this in
so
this particular case.
Right, okay. So the statement is that if you have simply connected space, you can look at its Quillen model, and you can look at the cofibrin model of that in DG Lie algebras. And the statement is that if you look at a modification of the derivation DGL of that is a Quillen model for the universal cover of B aught of the space.
Aha.
Okay? And the reason you have that is because this derivation Lie algebra satisfies the same universal property, but in the category of DGLs as B aught does. That's the idea. Okay. So that's what I'm going to say about one. And for the second, this heavily uses a certain vanishing theorem about cohomology of arithmetic groups in rational representations. So this is due to Borel. I'll just state it for the symplectic group, but it's, I mean, it holds for other arithmetic groups, for instance, the orthogonal group that becomes relevant in the when D is even. So it's basically the following statement that if you have, well, so this is 0 in the stable range for any non-trivial, irreducible rational representation of the algebraic group SP2G. That is defined over the rational numbers. The rational representations is in the sense of algebraic, representations of algebraic groups. Good. And the fact that this derivation, Lie algebra, is in fact a nice locally finite rational representation of the symplectic group. So that also is needed for to be able to to apply this theorem. Okay. Yes, and it also uses another thing. I guess I'll have to put it here. It actually uses, currently it uses injectivity of the map from the rational cohomology of the stable symplectic group to the rational cohomology of the stable diffeomorphism group. So, so we use so this is something you can prove. Using Oscar's and Søren's theorem, and this of course implies injectivity of the map from the cohomology of BSP infinity into B aught. But I don't have a direct proof of that. I have to go via the diffeomorphisms to actually prove it. So that's a little peculiar, and it of course would be nice if you could avoid using that. So
Alexander?
Yes?
Can I ask, in these two statements, where do you use that M as a manifold?
I only really use that it's a concurrent space. So I only need that the intersection form is non-degenerate.
So the statement that relating pi 1 to the symplectic group, for example? Pi 1 of B of aught?
Yeah, that should be true. Yeah. Okay, so this is what the current proof uses, but there should be this should be a consequence of something else. We don't want to put that here. So 2 should hold unstably it should be related to in some sense it should be related to equivariant formality of equivalence Lie algebra. So first of all, if you can make sense of this, because, well, pi 1 acts on the universal cover, but since equivalence construction involves, base spaces, you only get a homotopy action on this differential graded Lie algebra. Well, okay, I guess you can still make sense of equivariant formality, but I don't know how to prove it. But that would imply collapse of both these spectral sequences unstably. And so you wouldn't have to use this Borel vanishing or the injectivity of this map. But I don't know. The current models in rational homotopy theory only deal with simply connected spaces, and they don't incorporate actions of fundamental groups. So that's why I don't really know how to approach this yet. So that's the theorem, and what's the outcome in terms of the stable cohomology? So again, by applying this Borel vanishing theorem, there results an isomorphism of algebras so you get a tensor product of the stable cohomology of the symplectic group, tensor the stable cohomology of this Lie algebra. Let me give it a shorter name. Let me call this H sub G. So we can look at the stable Chevalier-Eilenberg cohomology of this Lie algebra. I should say also these Lie algebras include in one another when G increases. So so you can take the co-limit, and then you take the symplectic invariance in this cohomology. Okay, great. So now we just have to. Well, first of all, this has been computed, of course. So this is known by Borel's calculations. So Borel says that this cohomology. I mean, everything is with rational coefficients, as I said. This is a polynomial algebra in certain classes of degree 4i minus 2. And what are these classes? Well, the simplex. I mean, you have the real. If you put R here instead, I mean, you have the real symplectic group. The maximal compact of that is the unitary group, and these elements are basically the odd pullbacks of odd Chern classes. Okay, so what about this thing? So now there's a very well, to me at least, a surprising thing. So we calculated these homotopy groups, and then, ignorant as I am, I wasn't aware of that these Lie algebras had appeared before. So this Lie algebra derivations turns out to have been considered by Kontsevich in his work on graph homology. So, and he actually calculates this. So his statement is the following. So this is via graph homology of the Lie operad, and plus work of Köhler and Vogtman. It says that, and well, he considers the case when D. So I mean, you can look at this Lie algebra when D is equal to 1, when the generators have degree 0. So that's the Lie algebra he considers, and he calculates this symplectic invariance in the stable cohomology. But it's an easy task to regrade his description to arrive at the following. So this cohomology. By the way, this is only for D odd. I don't know the answer if D is even, but perhaps there is a graph homology interpretation. So this is only for D odd. So this is in fact a free graded commutative algebra on a graded vector space V, where in dimension K you have a rather bizarre thing. You have the sum over all n of the homology of the outer automorphism group of a free group with rational coefficients, as always. So here, this is the these are the outer automorphisms of the free group on m plus 1 generators. So it means that this cohomology contains, for all, this is for all, and it contains the homologies of all these outer automorphism groups. So
Wait, this is a rational calculation, or?
everything is rational, yes. So this implies that, for each homology class C in, say, HK of out Fn plus 1, we have a primitive class well, these are all hop families, as it turns out. And there's a primitive class that would, I don't know, I'll call it lambda C in this cohomology group of. So this is rather bizarre. So, compared to the description of the kappa classes, you started with a cohomology class in VSO2D, and then by doing some geometric construction, you arrive at the characteristic class. Now here is another way of producing characteristic classes from certain homology groups, but I have no idea what the geometric meaning of this is. So that is something I would like to understand. So note that, this of course goes via this Lie algebra and Kontsevich theorem, but of course, seeing this, you might wonder, there should be some direct construction from classes here going to characteristic classes here. But at the moment, I don't know how to do that. So, okay, but that's great. But so what can we say now about? So now all we have to do is go and calculate this homology, and then we know what the stable cohomology of B what is. So I talked to various people that have been working on this, and this idea sort of backfired because it turns out that this is a very mysterious group. Not very much is known about it. Not many classes are known. Let me tell you about some of the things I learned when talking to these people. And so they were asking me if I could if I could say something about this group in view of this isomorphism. So that might actually be what we should be doing. But anyway, let me just list some of the properties of the homology of out, and then I'll end by stating. Yeah. Let me just So here's some things that are known. The rational homology is 0 for unless k is in a certain range, roughly between n and 2n. So the precise range is 4/5 n and 2n minus 3. Okay, so yes. And then there are certain classes known. So Morita constructed cycles that are called mu R that give you potential homology classes in H4R out F2R plus 2, and he conjectured that all of them give non-trivial homology classes. So this is conjecture is apparently still open, and it's known only for R equals 1, 2, and 3. And this is one example of a family of classes. There has been recent work of so more cycles constructed by very recent work of Jim Conant, Kasabov, and Karen Folkman, and also another team, Morita, Sakasai, and Suzuki. So they have very interesting methods of producing cycles. But if I have understood the situation correctly, there are very few of these cycles that are known to be non-trivial. Okay, but then, so what should we do? I mean, so now I can tell you why I'm interested in the map. So I mean, so the question is now, can we detect the non-triviality of classes in the homology about Fn by using the map? By using this map and Sørens and Oster's calculations of the stable cohomology of BBIF. I mean, just sort of some simple checks shows that, I mean, in the relevant dimensions, there are lots of primitive classes here, lots of non-trivial kappa classes. But again, because the construction of these classes are so different, I mean, then we don't really understand this map yet. So one thing that it's maybe interesting to note is that this map is not injective. So there has been, by certain Euler characteristic calculations of these homology groups, they show the existence of odd homology classes in outer Fm. And so by our theorem, this implies that there exist odd, non-trivial, primitive cohomology classes in this. But here, everything is even dimensional. So in particular, this map is not injective. So it couldn't detect everything. But who knows? I mean, it's something that I think deserves to be investigated. And perhaps a final remark is that perhaps one should now try to approach the calculation of this cohomology by using the methods that are more similar to the methods used here. So, for instance, is it true that if you take the plus construction of B aught, is it true that that's an infinite loop space? And if so, can we identify the underlying spectrum? I think I'll end with that question. Thank you very much.